Welcome back. We are talking about the end stages of stellar evolution for a low mass star and thinking about the center of this star after its round of hydrogen, and the center, which is now helium ash, continues to get hotter and denser and contract until eventually the Pauli exclusion principle is met. And they just can't get any packed any tighter than that. And so something interesting and fundamental happens at this point. And that interesting and fundamental thing is this. So you have a normal star, and if you were to plot, let's say, the temperature of that star as a function of radius, it might look something like this. It's highest at the center, and it's going down and down and down and down, and eventually it reaches some point, reaches the surface. No matter what variable you're plotting here, if it's temperature, if it's density, if it's pressure, all of those things are getting higher and higher and higher until you get to the very center of the star. When the Pauli exclusion principle kicks in, something called degeneracy happens. And what degeneracy means is, again, any of these functions, let's say temperature as a function of radius, the outer parts look about the same. But again, this temperature is getting higher and higher and higher as the star contracts. And so what happens is the density and the temperature, all of them cannot get above a certain amount. And so what that means is there's a region of the center of the star that all has about the same density, temperature, pressure. And it's this that sets up something very different than where we were before. So let's go back to our slides. So the helium atoms are packed so densely that they have virtually the same density, pressure, and temperature at the center. And that's what that little cusp at the center of that thing that I showed in the graph was. All of the regions of the core have about the same density and pressure and temperature. Now, there comes a point when this thing gets so hot, 100 million Kelvin or so. Recall, the center of the sun at the moment is about 10 million Kelvin. This is 10 times hotter than it was before. Now, all of a sudden, helium can start burning in the core. But there's a fundamental difference between helium starting to burn in the core here than hydrogen starting to burn in the core when the sun was just reaching the main sequence. And the difference is this region that we just set up. When the sun's a normal star, when hydrogen began burning in the sun, it looked like that. Where did it start burning? It only started burning at the very, very center where it was hot enough and dense enough to actually start burning hydrogen and helium. When helium burning begins in the center of the sun, the entire center part of the sun has the same temperature and density. And so all this entire region reaches the temperature and density necessary to fuse helium at exactly the same time. And so this was a fairly slow process. This is an extraordinarily fast process. Once helium can start burning at the center of our star, it can do so everywhere at once. And this releases a huge amount of energy all at once, something that we know and can define as the helium flash. And that's what the flash means. It's happening everywhere at the sun at once, and it's helium burning starting all at the same time. And so this is we've been talking about very slow processes on the main sequence, evolving up the main red giant branch, the top of the red giant branch. The helium flash, conversely, is a very fast effect. It happens almost instantaneously. And so the structure of the star at the top of the red giant branch after the helium flash changes very quickly. All of a sudden, let's go back and think about our star again, and the center of our star again. Here is the center of our star. Let me erase these guys and think about what the center of our star actually looks like now. We've got the core of our star although the way we defined core before isn't really valid anymore. Remember, we had a region where we had a helium ash, right? So we were burning hydrogen there. This is immediately before the helium flash. And this region was just helium ash. There was no fusion going on there at all. All of a sudden, we start burning helium very quickly in the center of our star, right? Now, all of a sudden, this region of the star, which had not been generating any energy at all of a sudden generates a huge amount of energy. What does that look like? Well, again, all of a sudden, this region, which was being compressed because it didn't have any energy at all, is now generating energy. What does that do? That new energy that's being generated pushes out all of these other layers. So that new helium that's being generated, that energy creates more pressure, and that more pressure pushes the inner parts of this star outwards. Interestingly. Okay, so now we have the center of this part actually expanding. So we have a new source of fuel in the center, now helium. And now, but all of this region outside of that region has gotten pushed outward. And so the regions where we were burning hydrogen before are now cooler and less dense. And so you're generating less energy in this hydrogen shell than you did before. There still is a shell of hydrogen burning, but it's been pushed out and is no longer as hot and not burning as fast as it used to be. So ironically, even though we just get a new source of energy in the center, this helium burning, the total amount of energy that's being generated in the center of the star goes down because most of it's coming from this hydrogen burning shell. And the fusion rates in this region actually go way down. So that region, you're no longer generating as much energy, you're no longer pushing the outer parts of the star out as much. And so those regions that had expanded out to being half an AU or so in the sun, excuse me, now come back down. And so the luminosity, the overall luminosity of the star goes down, and the total radius of the star goes down a little bit. And our models say that the surface temperature of the star should come down a bit. So here we go, back to our slides. The core expands, meaning the very center of the part, center of the sun, center of the, where the helium burning is start. The total luminosity goes down because the hydrogen burning shell, the energy being generated there goes down. The total radius of the star goes down, and the surface temperature goes back up. Here is a better diagram than I was just drawing of what this might look like. This is on the left, a star and what it might have looked like when it was on the main sequence. You're burning hydrogen in the core. As it's a red giant, as it's moving up the red giant branch, this is the next stage. You have an inert helium core, no thermonuclear reactions going on. You have a shell around that where you're burning hydrogen into helium. And of course, the outer parts have expanded greatly. Once the helium flash happens, you are now burning helium in the core of your star. There is still a hydrogen burning shell surrounding that, but it is much smaller. It has been pushed out further now, and there's not generating as much energy. And the outer part of the star is going to come back and become a little bit smaller. This is a red giant after helium fusion begins. So these are what those three stages kind of look like. What happens to the star in the HR diagram? Well, it's gotten less luminous, so that means it has to go down on the HR diagram. The surface temperature has gotten hotter, and that means it must move back to the left on the HR diagram. It moves back towards the main sequence. We don't think it will actually reach the main sequence, but where it actually does go actually depends on a lot on how much mass you lose at this point. The star has gotten so big as it moves up the red giant branch that the outer parts actually become fairly tenuous. And these energetic events like the helium flash can actually blow out large chunks of the star. that are lost to it forever. So depending on how much mass is lost in that process, the star can settle in sort of here if less mass is lost, or if more mass is lost, then it will become actually, ironically, hotter and hotter. Although they all have about the same luminosity at this point. But anyways, certainly much lower luminosity and hotter than the star was when the helium flash began. What does this look like? When we look at an old cluster, we can actually see all of these phases of stellar evolution. And we can start to now understand all of these things, right? This is one of the reasons why clusters are so useful. They're a snapshot of what's going on. So here is an example of a globular cluster, a fairly old cluster, and we can see all of these stages of the main sequence, all these stages of stellar evolution there. These are the main sequence stars. There's the turnoff point. That's what gives you the age of the cluster. These stars are just running out of hydrogen. These stars are the horizontal branch. This is the red giant branch, or this is the subgiant branch down here. These stars have run out of hydrogen in their core and are having that central part, the helium ash core, slowly compress and get hotter and denser. And as that happens, the total luminosity of the sun goes up, the total radius of the sun goes up, and the total temperature, surface temperature, goes down. This star right here is just about to go helium flash. That's the tip of the red giant branch. It can't get any brighter. It's just about to ignite helium in the core. And once that happens, it very quickly jumps down to this line. You can see, for reasons that are obvious now, we call this the horizontal branch. The horizontal branch is the region of the HR diagram where stars are steadily burning helium into the next thing that it turns into. It's analogous to the main sequence. It is a fairly long-lived stage of stellar evolution. Not much happens to a star once it reaches here. It sits there and happily burns helium until it runs out of helium then in the core. So again, the red giant branch is an inert helium core with a hydrogen burning shell. The horizontal branch, you're burning helium in the core now, and you still have the hydrogen burning shell around it. Okay, here are some other examples of other clusters, and you can see how different these horizontal branches look. The main sequence, they look kind of different here, but that's only because there's a lot more stars and they're not as well measured. The main sequence is fairly well defined. The turnoff point is fairly well defined. These are slightly different ages of clusters also, and there's slightly different x-axes, but it's basically temperature. There's this branch, this is the red giant branch for both of them, the red giant branch for both of them. The tip of the red giant branch for both of them are almost analogous. You can make very clear analogies between these two clusters. But look at the difference in the horizontal branch, this HB thing. 47 Tuc is very short and stubby. Why is that? It's because not much mass has been lost. This cluster has a fundamentally different properties of this cluster. M3, a lot of mass has been lost, and you see a very extended horizontal branch that even turns down a bit. These are all horizontal branch stars. These are all helium burning in the center stars, as are these. So you can see just how different they look from cluster to cluster. But it's all the same phenomenon. This is the helium burning main sequence. This is the helium burning main sequence. Okay, so that raises the question, what is it that this helium is burned into? And that's where we come to this slide. So what happens? Helium burning happens via the triple alpha process. This is a bit of lingo, but it makes sense if you understand the lingo. Scientists use the word alpha to describe a helium-4 nuclei. This goes back to the days of the first particle accelerators that were ever built. How do you study atoms? Well, you basically throw them against the wall and break them apart and see what flies out to see what they're made of. And that's really what they did at first. And they had no idea what was going to happen. So they would take, I don't know, a lead nucleus or something heavy, smash it against something else, and see what came out. And there were three basic things that they noticed. There was one thing that was extraordinarily massive and energetic and was able to pass easily through things. There was another thing, and clearly had charge. There were other things that came out that were very low energetic, very low energy, very low mass, and had a negative charge. And the third thing that came out had no charge at all. Well, they named them alphas, betas, and gammas because they didn't really know what they were. It turns out later on that alphas are helium nuclei, betas are electrons, and gammas are photons, which is why we call them gamma rays today. So you sometimes hear electrons referred to as beta particles, and you'll often hear these helium-4 nuclei referred to as alpha particles. Anyway, so the triple alpha process is three of these helium-4 nuclei fusing together to make a single carbon-12 nucleus. Now, as you probably know, you can't bring these three together at the same time, just like you couldn't fuse hydrogen into helium all at once. You had to go through stages. The triple alpha process is a two-step process. We'll go through it real quickly right now. The two-step process looks like this. So you've got, we can do this as we did before. Here's a two helium-4 nuclei, protons and neutrons. They come together, nuclear physics happens, and out the back end comes, this is step one of the triple alpha process. Out the back end comes an atom that has 4 protons and 4 neutrons. They probably aren't arranged like this, but it doesn't really matter. So if we're keeping track on our equation line, it would look like this. A helium-4 nucleus plus a helium-4 nucleus goes to a nucleus that has 8 nucleons. It's going to be an 8. And the question is, what is this atom that has 4 protons and 4 neutrons? Well, you can look it up. The element whose atomic number is 4 is beryllium. So this is a beryllium-8 nucleus. Now, this is an extremely short-lived nucleus. Beryllium-8 does not like to exist. These alpha particles are extraordinarily low energy, and matter likes to go into its lowest energy state. And so this is a higher energy state. This will almost immediately always decay back into 2 helium-4 nuclei, 2 alpha particles. So this is going to happen 100 times, and 99 of them, this beryllium-8 nucleus is going to decay back into the things that it started from before it has a chance to do anything else. But maybe one time in 100, I'm making that number up, but some small percentage of the time, this beryllium-8 nucleus, before it has a chance to decay, can get hit by another helium-4 nucleus. Remember, there's no hydrogen around anymore. So these helium-4s are the most common thing around, and they're the lightest and easiest to make the reaction happen. So if that can happen, nuclear physics happens, and out the other side comes a nucleus that has 6. Oh, by the way, I didn't mention this. Are we good here? Have we satisfied all of our conservation laws? Well, charge conservation is good. We have a +4 and a +4 out. So that's really all we need. There's no other thing that has to happen here. We're in good shape. So here, we're combining one of this beryllium-8 nucleus with a helium-4 nucleus. We get 6 protons and 6 neutrons. Again, they're not going to be arranged like that, but that's sort of for illustrative purposes, not bad. So this beryllium-8 nucleus, again, before it has a chance to decay, bangs into another helium-4 nucleus. And you get, at the other end, an atom which has 12 total nucleons, 6 protons and 6 neutrons. So the number is 12 up here. And an atom which has 6 protons in it. You can look it up on your trusty periodic table, which I'm sure you carry everywhere with you, is a carbon nucleus. And so in the end, we have taken this helium nucleus and this helium nucleus, made a beryllium nucleus. We've added a 3rd helium nucleus, the triple alpha process, and we get out in the end a carbon-12 nucleus. And again, we're good to go as far as our conservation laws go. Same number of nucleons, same charge. We don't need anything else coming out on the other end. There may be some things like gamma rays, but they're not all that important for understanding the reactions. The bottom line is 3 helium-4 nuclei converting into a single carbon-12 nucleus. Okay, here we are. And we've gone through the 2 steps now already. Okay, I will stop there and we will think about what happens after the sun runs out of helium in the core in the next video.